Hello and welcome to this fourth lecture on purification and separation methodologies. In today's lecture, we will continue our discussion on chromatographic methods and try to learn some new concepts. We will begin with a concept of resolution. Then we would move forward and discuss selectivity issues and concept of selectivity in chromatographic separation. And towards the end, we would define a new term, capacity factor, and try to understand it. So, we start with a few terms. This is a typical chromatogram, which is this graph of detector's response as a function of time. Instead of this time, one can also use eluent volume in this x-axis. Now, there are two things to look into. First is this injection point. This point signifies the point in this time reference where the injection has been made or solute has been added to this column. This is the peak of interest. Now, the distance of this peak of interest from this vertex of this peak to this injection point is Tr. This Tr is called retention time, which signifies the time taken by a solute to reach detector from the point of injection. This retention time can also be related to a corresponding volume. As I said, this volume can have on this x-axis instead of time, and this corresponding volume is called retention volume. A ratio of this retention volume and Tr, which is retention time, provides the flow rate of the solute, and I want you to keep this term in mind. Next, in the same chromatogram, there is another peak which is called a non-retained solute, a peak corresponding to non-retained solute, which primarily means is that solute which just would not interact with the column and would come out with the mobile phase without any interaction. That also indirectly means it is the mobile phase, the time taken by the mobile phase to come and pass through the column. It is denoted by Tm, and this Tm is also called dead time. It is the time of travel of a non-retained solute through the column. There is one more term which we need to know, and it is called baseline width, which is denoted by W. As you would know, this baseline width denotes the width of a solute's chromatographic band at the baseline. The way we measure and evaluate this W is one draws a tangent from the point of inflection and then measures up this W at the baseline. So, this is about a few terms which are important for us to derive certain equations and to know this chromatography in more details. The significance primarily of both these terms, retention time and baseline width, is that it would help us determine the strength with which a molecule is retained on the column. So, indirectly it tells us both these terms about the interaction of mobile phase of the solutes with mobile phase and with the stationary phase. So, next move on to the next point in discussion, which is resolution in chromatography. Resolution per se is the degree to which it is possible to distinguish between two adjacent objects. Now, as in these two figures, in one image resolution is not so good, whereas in the other case resolution is pretty good. In chromatographic terms, what do we mean by resolution? Resolution in chromatography, which is denoted by RS, it measures separation between two chromatographic, or I would say adjacent chromatographic peaks. For example, you have a solute mixture containing 3 peaks or 3 solutes. Now, a chromatogram would appear as 3 peaks, peak 1, 2 and 3. Resolution would ensure how well the two adjacent peaks, peak 1 and 2 or peak 2 and 3, are resolved or separated or distinguishable in a chromatogram. As the example shows in these two images, the first image is 2 components which are not well resolved. They are not well distinguishable. Hence, we would say they are poorly resolved. Whereas in the next case, these 2 peaks are quite well resolved, and hence we would say the resolution of this chromatogram is better than the resolution of this chromatogram. We would need to understand more about chromatographic resolution through certain mathematical derivations and equations. Let's do that. As a reference, we will take the same image of 2 elutes. This is elute A, which has a baseline WA, and the second elute having a baseline width WB. The corresponding retention time, which in this case is adjusted retention time for both the peaks, it is TRA for this peak A and TRB for this peak B. I just mentioned this term, adjusted retention time. What is adjusted retention time? It is the retention time of a peak which is minus the retention time of an unretained solute. So, in this case it would be TRA minus TM, which would give you adjusted retention time, which is this. Now, resolution would be equal to delta TR, which is the difference between retention times of TRB and TRA. This difference upon W average. W is baseline width, we have already seen. So, this W average is the average of baseline width of the 2 peaks in question, for which we are seeing resolution. All right. Now, putting this value into this equation here, delta TR upon W average, we get resolution equals to twice delta TR upon WB plus WA. So, that is the equation of resolution. What is the significance of this equation? RS equals delta TR upon W average, or it is twice delta TR upon WA plus WB. Now, this equation shows us that resolution RS is directly proportional to delta TR, which means this delta TR is related to something which we call separation factor, which is denoted by alpha. And this separation factor is related to selectivity of a particular chromatographic experiment. What do we mean by this selectivity now? Again, I take your attention, draw your attention to these 2 chromatograms. Out of these 2 chromatograms, this first chromatogram is less selective vis-a-vis any of the 2 peaks. As you would see, that both the peaks are quite close to each other. In its comparison, the second peak, the second chromatogram, it seems more selective as the two peaks are quite a distance apart. So, what we really mean by selectivity is how selective is your particular chromatographic experiment is towards a particular peak, right, and RS resolution would be directly proportional to this factor. Hence, what we can say is higher the delta TR, it would mean higher would be the separation factor alpha, and that would mean higher would be selectivity of that particular chromatogram. This is one aspect as far as significance of resolution is concerned. The second aspect is, as you would have noted down, that this resolution RS is inversely proportional to W, right, as this equation suggests. So, what does it mean? This W is related to what we call as peak broadening, right. So, more is the W, more is the effect of peak broadening, and then this peak broadening is related to efficiency of a particular chromatographic experiment. What do we mean by that? Now, ideally what a chromatographer would always envisage is this chromatogram shown here. In this, as you would note, the eluating peaks have come out like very sharp lines here. This is an ideal situation, and as you all know, ideal situations rarely exist. Hence, what we generally get as a normal chromatogram are such kind of peaks which are, instead of having these sharp lines, they are Gaussian shaped curves. Why would that happen? That happens because of this effect of peak broadening. Now, as far as the reasons for this effect of peak broadening in the context of chromatograph or chromatography is concerned, we would take it up in a little more details in the following lectures. But irrespective of a chromatographic separation, this phenomena of peak broadening is also governed by some laws of physics, and those laws are law of laminar flow. What it shows is that if there is a solute plug in a moving liquid, so as the time progresses, one would note that some of the particles in that solute plug will start to move ahead and some of the particles will start to lag behind. That is the phenomena of laminar flow, and based upon that phenomena, which has to do something with the diffusion properties of the solute, the peak broadening would always occur. So, let us look at it one more time. The point we are trying to say here, in this chromatogram, as the peak width would increase, peak broadening would increase as this W is increasing here, and with peak broadening efficiency would decrease. So, to summarize this, I would say we have now identified two important terms with a chromatographic experiment. One is selectivity and the other is efficiency. We have related selectivity with TR. So, more is delta TR, more is the selectivity of a chromatographic experiment, whereas we have related efficiency with this term W. So, more is W, less is the efficiency with that particular chromatographic experiment. Combinedly, both these terms are integral parameters for resolution, as is being shown here. So, ideally what we would want a chromatographic experiment to be selective and efficient, which would mean we would want more delta TR and less W, and that point must be always borne in mind. All right. Now, we are moving on to another term which is called capacity factor, another very important term as far as chromatograms and chromatography is concerned. So far we know that a separating factor or selectivity factor alpha is related to delta TR. Now, it is time to look at it in a little bit more details. So, alpha is actually equals to, we are talking about two peaks, peak B and peak A, right. So, it is equal to TRB minus Tm, which is adjusted retention time for peak B, upon TRA minus Tm, which is adjusted retention time of peak A, which then is equal to this Kb upon Ka. Now, this is your selectivity factor, and these two terms we are introducing for the first time are called capacity factors or retention factors of respective peaks. So, in this particular case, Kb is capacity factor of peak B and Ka is a capacity factor or retention factor of peak A. This capacity factor K describes the flow rate of a solute on a column, and it is actually given by TRA minus Tm upon Tm for peak A. Okay? So, which means adjusted retention time upon time of unretained solute. This is capacity factor. Now, let us try to understand this, what this term is signifying by this equation. It shows that how well a solute in question has interacted with a stationary phase. So, a more a solute would react or interact with a stationary phase, more would be this term TRA minus Tm, and more would be a capacity factor or retention factor. So, it means how well a solute is retained onto a stationary phase. So, this is the term, and what is being found out that there is an ideal range of Ka, the value of Ka, if one is looking at a good separation of a peak or good selectivity of a particular peak. Let us consider two different situations here. In the first situation, in this equation Ka, let us assume that the value of Ka turns out to be less than 1. If that happens, it would mean TRA minus Tm is less than 1 here, which would mean that TRA is more or less equal to Tm, which would mean that the peak in question has come almost at the same time when an unretained peak has appeared. It means it's a case of fast elution. I would say very fast elution, which we do not want, right. So, let us consider the second case now. In the second case, let us suppose this K comes out to be far greater than 1. This K is Ka, it can be any K about the peak in question, right. Which means if it is far greater than 1, it means this term is far greater than 1. It means TRA or a particular retention time in question is far greater than Tm, and that would mean that elution has taken an unusually long time. Now, try to understand that. If you are running a chromatographic experiment, you do not want your experiment to be just completed and your solute not having interacted with the column, right? That you do not want. At the same time, you would also not want that your chromatographic experiment is run and is being run for the whole day and nothing comes out. So, both the situations are unwarranted for us. What do we actually desire then? What is a chromatographer's goal? And a chromatographer's goal is then to optimize resolution and minimize time. And using this concept of K, one should be looking at a range of k between 1 and 10. If it is less than 1, elution is very fast. If it is greater than 10, it means elution is taking unnecessarily long time. So, as a chromatographer, you can always try to fix this value of k between 1 to 10. Now, the next point is, how would you do that? How would one fix a value of k between 1 and 10? And that is the point we need to understand, and we can understand if we know solute interactions with the stationary phase and also with the mobile phase, right. So, some of the solute interactions with the stationary phase we have already discussed in the previous lecture, like adsorptions and ion exchange and other things. Primarily, a solute would interact with stationary as well as mobile phase through some feeble forces like dipole-dipole interactions, like hydrogen bonds, dispersion forces and pi-pi interactions, right. And these interactions needs to be managed if one needs to have a grip on k, all right. So, what can be done on a stationary phase if one needs to control k? These are the two things which can be done. You can select a type of column packing, or secondly, one can select the temperature of the column, which is of more importance in gas chromatography than in any other chromatographic systems. As far as mobile phase is concerned, one can govern the type of solvent and one can also look at the solvent strength if one needs to have a grip on k or the capacity factor in order to get a better selective chromatogram. Let us try to look at these interactions in some details. Now, as far as solvent or elution strength is concerned, we have already seen how eluent strength has a role to play as far as chromatographic elution or separation is concerned. What is the significance of eluent strength? That we will need to see. In a normal chromatograph or in a normal chromatographic experiment, the more polar solvent one would take, it would mean higher would be the eluent strength of that particular mobile phase, and that would mean lesser would be the retention time of the solutes in question, which would then mean lesser would be the capacity factor. As we know, capacity factor is directly proportional to retention times, and most importantly, less would be the selectivity of that particular chromatographic experiment, and lesser would be the resolution, since resolution is also directly proportional to retention time. Now, the second thing, as I said, it is not only always about eluent strength. Sometimes the solvents having same eluent strength can also impart different selectivities on an chromatographic experiment. Let us see how with one example. It is because different types of interactions are involved, and the example in hand is diethyl ether and dichloromethane. Both have similar strength, but both impart different selectivity just because of some physical chemical properties of these two solvents. Now, considering stationary phase, let us discuss about the column temperature, how it imparts and influence selectivity. So, more is the column temperature, lesser would be the retention time, solutes would come out faster, and likewise lesser would be the capacity factor, less would be selectivity, and less would be resolution. So, that is something a chromatographer can always keep in mind if there are selectivity issues in hand, whether you need to cool down the column or whether you need to heat up the column. As far as column packing is concerned, that is another aspect which we have already discussed in details in the last lecture. You can pick out from a range of normal phase columns or reverse phase columns, and there are plenty of different materials available in both the kinds, in normal as well as reverse phase, and one can always pick and choose different columns to modulate selectivity and resolution. As a chromatographer, I throw this question to you: What would you like to modulate? What is easy to modulate, whether a column or the mobile phase? And the answer would be very straight. It is the mobile phase which is easy to modulate, and that is what we generally do as chromatographers in order to impart selectivity on a chromatographic column. So, next time when we meet in the next lecture, we will be discussing about efficiency of a column. We would also be talking about peak capacity of a column and how we can optimize a chromatographic separation. I hope you enjoyed this lecture. Thank you very much.